Hey everyone, thanks for tuning in. In this short presentation, I'll give you an overview of our paper called From Shadows to Safety. The name already hints at what it's about, making AVs safer in situations where parts of the scene are occluded. Think of parked cars or a building blocking the view. Those blind spots can be risky, and we've come up with a way to handle them better. So let's jump in. Let's start with a simple example. On the left side of the slide, we see a cyclist approaching the intersection, but they are completely hidden behind the orange vehicle. Our blue car has no chance of detecting them right now. A few seconds later, as shown on the right, things get tricky. The cyclist enters the intersection just as our car might be about to drive through. If both parties continue, there is a real risk of getting dangerously close or even colliding. That's exactly the kind of situation we want to avoid. And to do that, the car needs to understand not only what it sees, but also what it can't see. Occlusions don't just exist in simulations. They are common in everyday driving scenarios. For example, in these two real-world videos, you see how quickly and unexpectedly road users can appear from behind occluded areas, leaving very little reaction time for drivers or automated systems. Clearly, addressing occlusions proactively is essential to ensuring the safety of autonomous vehicles. Let's briefly look at what's already out there. A lot of work has been done on modeling occlusions, from POMDPs and reachable sets to infrastructure-based perception and even phantom agents. But in practice, many of these approaches come with challenges. On the right, you see some common limitations. Scalability is an issue when behaviors get diverse. Real-time performance can be a bottleneck, and VR use, like cyclists or pedestrians, are often underrepresented. That's where our approach comes in. We developed a modular, open-source framework that combines occlusion tracking, agent-centric modeling, and risk metrics, all designed to support a comprehensive and realistic safety assessment. Here's the full framework, but for now let's focus on the main interaction between the motion planner and the occlusion awareness module. Everything happens within a simulation environment, where we define the scenario and parameters. This sets the stage for the motion planner, which takes into account the vehicle's current state and creates possible trajectories. So the motion planner starts by generating a set of valid and cost-optimal trajectories based on the current scenario. These trajectories are not final yet. They still need to be checked for safety. And that's where our occlusion awareness module comes in. The planner passes all the trajectories to our module, and it evaluates each one with respect to potential hidden dangers in the environment. We'll go into the internals of the occlusion module on the next slide. For now, just keep in mind that it adds an additional layer of safety checking before any trajectory is selected. So, let's take a closer look at how the occlusion awareness module works. It all starts with occlusion tracking. So, we don't just look at what's currently hidden, we also track how visibility has changed over time. So, if an area was visible a few moments ago, we know that only something moving at a physically plausible speed could have entered it. And that gives us a more realistic view of where hidden agents might be. Based on that, we generate phantom agents, hypothetical road users like cyclists or pedestrians in those occluded regions. We assign each of them a set of possible motion behaviors. And finally, we take all trajectories from the motion planner and run a safety assessment. We evaluate various risk metrics to assign a safety score to each trajectory. And the final result is a risk-aware motion plan that takes both visible and invisible hazards into account. Here's the first example where a truck is blocking the view of an approaching cyclist. On the left, you see the velocity profiles for different planners. Let's focus on the black and orange lines. The black one is our method, and the orange one is the baseline planner without occlusion awareness. You can clearly see that our planner slows down before the cyclist even becomes visible, thanks to the phantom agents and the safety check. The baseline planner, by contrast, keeps going too fast and ends up in a collision. On the right, you see visualizations from our simulation. The upper one shows the safe trajectory with our method, and the lower one, the unsafe plan of the baseline planner. Additionally, let's take a look at how different risk thresholds affect the planner's behavior. In this case, there was no real object in the occluded area, but we still test how cautious our system acts. The plot showed that with lower thresholds, the vehicle slows down earlier and drives more conservatively. You can see how the baseline planner, in this case the dashed line, maintains higher speed, but that comes with a much higher risk. If there had been an object, the situation could have been critical. So the takeaway here is we can tune the planner's level of caution through the risk threshold, which gives us flexibility depending on the use case. And finally, let's look at the effect of occlusion tracking over time. The plot shows how much of the scene is considered occluded, with and without tracking. The blue line without tracking is much higher. That's because every hidden area is always treated as potentially dangerous. But with our tracking system, the black line, we can rule out many regions based on visibility history. If something hasn't been visible recently, we know it can't just magically appear there. That helps reduce uncertainty and lets the planner focus on areas where actual risk exists. Again, we have a short animation that shows this dynamic behavior in action. To wrap things up, our module helps make autonomous driving safer by proactively reacting to occluded areas and reducing risks around blind spots. By combining occlusion tracking over time with diverse phantom agents and a broad set of safety metrics, we get a much more realistic view of potential hazards, without being overly cautious. Looking ahead, we want to improve real-time performance by moving from Python to C++, and we aim to integrate our module more tightly into the planning process. We are also planning to extend the framework with traffic rules, semantic understanding, and more complex scenarios. And our key takeaway is, from shadows to safety. Our method enables safer autonomous behavior in occluded environments by combining occlusion tracking with agent-centric risk evaluation. That's it from our side. Thanks a lot for watching. If you'd like to dive deeper, check out the links on the left. You'll find the preprint of our paper, the source code on GitHub, and more information about our team and our projects at the lab website. We are looking forward to your feedback, and feel free to reach out if you're interested in collaborating or trying out yourself.